Hello, we are team number 3, Rocket Eagle Lander, and we will be presenting our IVVT plan of the course System Integration, Verification and Validation, taught by Dr. Amit Joe Lopes. The team members are Valeria Mendoza, Jose Rivera, Montserrat Salas Nava, Neil Smith, Rayfield Velasquez, and myself, Cesar Franco. Contents of the Relander IVVT plan. We will be reviewing the concept of operations, the requirements verification matrix, the risk management and defect log, test case description, integration phase, qualification and acceptance, reliability, maintainability, and availability, and at the end we will be getting into a conclusion.
The concept of operations by Group 3. The CONOPS. The Relander system is a human-rated relaunchable vehicle and rocket that provides the means for human space travel for an out-of-world experience. The diagram on the right depicts a typical launch and re-entry for both the Icarus rocket and the Daedalus capsule. The conceptual diagram is also depicting the satellite relay to be utilized in order to successfully communicate with the Mission Operations Center.
Hello, my name is Montserrat Salas, and I'll be talking about the requirements specification for this project. When talking about requirements, the first step prior to doing anything else is to create a requirement analysis to encompass the detailed needs of the system. We do this in order to ensure that the final developed system is going to perform as requested by the stakeholder or the customer. In the case of this project, the main objective was to create a capsule or space rocket that would serve as a method of transportation to bring humans into space and back. Therefore, we created a list of requirements that aim to create or generate conditions under which each requirement could be tested to increase safety, achieve optimal system performance, as well as reliability and usability. And just like it is mentioned in the PowerPoint, creating a systems requirement specification list, it's going to allow for you to describe the features and expected behavior of the system. Moving on, after all of our requirements had been specified, we went ahead and created a requirements verification matrix. When developing requirements, it is really important to identify an approach for verifying the requirements that you have just set for your system. If you look at the image that has been provided in this slide, we have a clear example of what an RBM should look like. This matrix defines how all of our requirements are going to be verified. You can see that we have a list of our requirements, and each one of these requirements has to fall under a certain category, which are the ones highlighted in green. We have definition, design, implementation, integration, qualification, component, subsystem, and system. So every single requirement will fall under one of these categories, which is what I was just mentioning. Another thing to mention when talking about RBM is that the matrix should identify each shell by a unique identifier and be definitive as to the source. Lastly, in regards to requirements, an RBTM was created, which is nothing else than a system requirements bidirectional traceability matrix. What the RBTM is a document that links requirements throughout the whole validation process. The purpose of the RBTM, it really is to ensure that all requirements that were defined for the system will be tested according to the test protocols that have been set already. Moreover, the traceability matrix is also a really helpful tool for the validation team because it'll help them ensure that the requirements will not be lost during the whole project. For our case, we used a bidirectional traceability matrix, and we have forward traceability and backward traceability. Forward tracing the requirements to their elements, it's going to help to ensure the completeness of the product requirement specification, and therefore ensuring that each requirement will be implemented in the system and that each requirement was thoroughly tested according to test protocols, which is what I was mentioning earlier. In addition, it'll allow to trace forward changes associated with requirements and any other requirements impacted by such change, and therefore preventing an incomplete implementation of the change. On the other hand, backward tracing each unique element back to its associated requirement will allow to verify that the requirements were kept current with the design of the system, ensuring that the scope of the project did not expand by adding elements that were not there initially. And also, backward tracing will help us trace back to defects in the design requirements.
Hello, my name is Ray Velasquez, and I'll be discussing the risk management and defect logs. Slide 9. Slide 10. Risk matrix. The purpose of a risk matrix is for the advantage of the risk matrix is for the project to understand what is the risk solution, to visualize and to comprehend what is the most damaging part of the project, to review and analyze and to assess what is the most critical asset that will damage the project, to identify the most hazardous part and decide whether the magnitude which will be damaging to the project. There are 5 steps to assess the risk for the spacecraft, which would be identify hazardous, decide whether the magnitude would be harmful, assess the risk, make a recording of the findings, and review the risk assessment. Now, part of that matrix would be to create a 5x5 or a 4x4 square box to understand the level of a risk that will be identified, to how the risk would be ranked to the importance of a high impact or to a low impact, and therefore it would be evaluated. Slide 11. Failure mode effects analysis. Now, the purpose of this is to take into account the action to eliminate and reduce the failures from the beginning, and understanding to the highest priority to the lowest priority of the modes of the effects of the acknowledgement of the project. Now, this is created by creating a table graph spreadsheet and analyzing what would be the highest priority into the lowest priority. And we have an example here of a circuit level, circuit board transistor. And we have here translator 1, 2, and also a pin 1. And we can see here the failure modes and also the next effect and the final effect, and how it's translated into a course document knowledge and the action regarding the risk of failure for the use of continuous improvement using this model, and is being identified into the failure levels and also into the intermediate effects and how it will affect into the modes. Next slide, slide 12. The defect logs. The purpose of a defect log is a document used to record all defects that occurred while testing and creating parts for the project. Now, the purpose of this right here, you can identify it in 3 areas. It could be labeled as the identifying the critical risk, also estimating the impact, and also minimizing the expected impact. Now, when looking upon identifying the critical risk, that would be identifying the critical risk in the system which will impact more if it occurred during the testing or in the stage later upon. Now, also in the defect impact, it would be estimating impact for each critical risk, calculating how much it would be for the financial impact. Lastly, the minimum impact would be once you identified, it would be all of the critical risks that would take action for the risks that may be harmful to the system that would impact to minimize or eliminate the risk for the risk which it cannot be eliminated. Now, as you can see here, we have a chart that identifies the management process on how it would be if the log would be in place. Now, the defect prevention, the deliverable baseline, the defect discovery, the defect resolution, and the process improvement, and the management process. Now we have a flow on how it would be and the reporting level from start to finish on how the reporting basis and the documentation process would be when recording the logs. Now normally we would use a spreadsheet or how identifying the prevention would be. Now it is the best method to eliminate the defects in the earliest stages of the testing instead of finding the defects in the later stages than fixing it. Now this method is also the cost effective as the cost is required in fixing the defects found in the earliest stages. Now I think however it's possible to remove all the defects, but at least at a minimum it would be the best way to always document in a spreadsheet on what the defects are and where is it located and how the cost effect would be to the project.
Hello, my name is Cesar Franco and I will talk about test description, text execution, and reports. Component test. The B&B planner shall determine and plan for coverage analysis. 4 different ways of acceptance test can be considered. The first one, factory acceptance test. This is a performance test to be executed for the transmitters and receivers at the factory. Performance specification sheets to be included with the equipment for reference. Second one, stage acceptance test. Integrations of the communication system must be tested to verify correct interoperability. Examples of the systems can be transmitters, receivers, up and down converters. Third one, verification test. We can verify if the system is able to communicate from ground. We can also verify performance by testing at maximum data rate capacities of the uplink and downlinks. We can verify negative test cases with illegal inputs work as expected, and timing and quality of the data communicated to the models. And the last one, the final acceptance test. First flight test will be the final acceptance to allow the commercial use of entertainment for scheduled on-board space tourists. Test execution and reports. The daily status report is one of the test execution reports that contains information about the different tasks performed, tasks executed, issues logged, and obstacles faced by the tester. Every member of the testing team creates a daily status report and sends it forward to their test manager at the end of the day. So we can say that the status report consists of updates related to different tests performed, tasks for the next day, and setbacks found during the day. Testing reports. We have 3 different types of testing reports. I will be explaining each one. The test plan status report shows the current status of the test plan and also notifies the team for change being made or revisions being implemented on the plan. The test documentation status shows the status of the test cases and test scenarios while the project is still under design phases. The test execution status shows number of test cases passed, failed, blocked, or not executed. Basically reports the status of the overall testing to the teammates involved. Basic concepts of test execution reports. These basic concepts can broadly be classified into 3 categories. The test report summary, which provides a brief overview of the overall execution status. The test scenarios, and list the different scenarios and test cases executed during the testing cycle. You can even find the name of the testers along with a brief description of the issues found during the execution. Reported bugs. This is just a defect list with a brief description of the issues. Steps to reproduce are mentioned for each. You can even mention the priority and if the issue is already assigned to someone. And for last, an optional section is the hurdles or implement phase. This is an optional section and you may or may not add it to your test execution report. This section is used to bring into focus the pain points and impediments encountered by the testing team during test execution. A good example can be issues with the test environment. The details and the outcome of this problem should be noted. This will outline the problem and the impact of the overall testing.
My name is Neil Smith, and we're going to be going over the integration phase for the RE lander. The first part for our integration test phase is to start integrating a built-in test into our RE lander. For this phase, we decided to pursue a built-in test to monitor the life support system, which provides oxygen into the capsule. This oxygen must monitor that the gas tanks are keeping the capsule at a pressure of 5 psi of pure O2. And this built-in test will monitor that. This is an online and concurrent built-in test, so it will be monitoring the performance while the RE lander is online, so as to send error messages and to send performance data to ground control, which is how it connects to the communication system. The benefit justification for pursuing this built-in test is that it mitigates the risk of non-conformance to requirement 15, which is the system shall carry 33.6 kilograms of oxygen. If this was not conformed to, then there'd be a lack of oxygen to the passengers, which can lead to the loss of life. We can see the reasoning behind this in our cost benefits analysis. There's an exposition value of 30 out of 100. It has very high impact, a little bit low risk, but we need to make sure that the impact doesn't occur. And the verification cost is only 5,000, but the impact cost is very high, so we get a lot of leverage focusing on this built-in test. It also focuses on requirements 6, 7, and 15 and traces to those, and you can read through those to see how it connects back to the performance. After we installed our built-in test, it will send information back down to ground control as part of the test. And information includes a bunch of many error codes which are labeled and which for brevity. And these include possible errors with the system, such as the secondary oxygen tank has a decompression problem, and it goes through a range. There are more than these, but this is a good example of what we'll cover in our built-in test. And the exact test results is that it has the correct monitoring. So it's able to send the correct error code once tested, and it also tests proper functions. So those satisfy the exit criteria. Our second phase of our integration test plan is to do an integration test of the communication system and propulsion system. So what is in scope is that direct linking between the communication system and the propulsion system. What is out of scope is the satellite relay system for the communication system. It's only the information that goes in and out. And this integration test involves an interface, information interface between the propulsion hardware and the communication software. So when the propulsion system gets info from the communication, we're going to see hardware results such as the actual fuel being dispensed. And part of our integration test strategy is that due to the high amount of cost of building physical prototypes for a rocket ship, due to the high risk and large scale, it's best to first do the integration test in a virtual laboratory, such that we reduce the costs. We can perform many different experiments, and once we have those verified and validated, then we can move on to the physical testing. And here we have the entry criteria for our integration test strategy. The entry criteria is that the communication subsystem and the propulsion subsystem have both been verified in their own component testing. This is to make sure that no defects start propagating into the integration test when we start combining the two systems together. And the test and part of the tests is that we test both systems to get a response. So we need to make sure it's from the integration testing rather than the actual component testing. So our test strategy, it is again information interface. So the test will involve input-output, and it also involves the software hardware. So we're not only going to get software inputs and software outputs, but we're going to see the direct results of those in the propulsion response, which is measured in test 2, which is a test involves direct input that will direct to the correct propulsion response. And the way that this works is that first we're going to not waste rocket fuel, make sure that it is functioning correctly, and then once we have that verified, then it will go to the actual, we're going to be using some rocket fuel in order to measure that the hardware response is actually correct as well, that the propulsion component is working as intended when integrated with the communication system. The last test which is necessary is to make sure that false input or noise input does not result in any propulsion, because this can lead to many errors during flight, so this also needs to be verified. And our final slide for the integration test phase is the results from this, which basically shows the pass-fail criteria and the integration tests that were performed. And through this we've encountered pass-fail, and we have passed all of these tests, which is completely necessary for such an important system and such an expensive system, to make sure that the verification is complete to move forward to the next phase.
Hello, my name is Valeria Mendoza, and I'm going to talk about qualifications and acceptance. The purpose of communication system is to handle the navigation and relay information from ground control to satellite relays to the rocket. There will also be communication subsystems relaying information within the rocket. For integration entry criteria, all components are acquired before the testing. The compatibility between components must be verified from an analysis perspective first, and there is communication capability with ground control. The integration strategy will be taken from a bottom-up method. The subsystem integration sequence will be integrated with individual connections first, then groups of communication connections simultaneously. The integration test exit criteria has been completed when the communication subsystem has full capabilities of functions. It also will have a minimized failure rate, and the functional test will be communicating emergency data, diagnostic reports in lifetime, and the successful communication of navigation control and data. The tools and equipment required are computer workstations, communication measurement devices, oscilloscope, host operating systems, and noise generation machine. The test types identified are satellites relay communications, the secure networks, which includes encryption, security keys, etc., access identifications and clearance, broadcast range, which means having a clarity of the messaging, and emergency messaging tests. The problems perceived are the time required to complete tests, the late delivery of hardware needed, delays in communication caused by system test failures, the unavailability of subsystems to complete communication and the delivery of them, communication synchronization issues, test-associated costs, and the final modification costs, which include the necessary modifications after the testing. We also have an environment needed, which is Virtual RF System Simulator, which utilizes tools to simulate and model the subcomponents that make up the communication systems, minimizes the amount of time needed to schedule tests on live systems. Number 2 are the control end-to-end testing environments, which are used to evaluate the communication systems from the ground station antenna to relay satellite to systems on the capsule and rocket. The end-to-end might be used for testing pre-launch by scheduling test time to verify correct antenna positioning. And number 3, operational live environment, which is testing the capsule and rocket communication systems live during the first launch for final system integration. Then we have 4 plant qualification tests, which include number 1, test levels. Those will be conducted on the high resolution level of component to component to observe good connection between each component. Tests will be taken on communication subgroup to subgroup in order to observe good coupling. Then the entire system will be tested with navigation and satellite relay to observe clean communication. Number 2 are test classes, which include functional tests of each component, interface testing, timing testing, load tests, erroneous input tests. Number 3, test conditions, in a contained lab and in the field to simulate weather conditions. Number 4, data recording, reduction, and analysis. The data recorder will be yes or no inputs on pass or fail. The load test will have a volume of data per second. And finally, we have a functionality for requirements test strategy. For requirement number 1, we induce a malfunction onto the system to ensure communication is still established with the satellite relay communication systems. For requirement number 4, we send data through communication modules to the satellite relay communication system to ensure compatibility. For requirement number 5, we simulate a random failure in the system to observe if the communication between the system, pilots, and ground controllers work. For requirement number 6, we simulate a mission for a few hours and ensure retrieval of data from all systems. For requirement number 7, we run a simulation of systems, components, degradation, and ensure communication systems notify of all maintenance requirements. For requirement number 14, we coordinate communication systems to ensure safe landing of the rocket and successful communication between them. For requirement number 17, we ensure the system's operating procedure, mission control, and tracking network support plan are followed by all the communication systems. And finally, for requirement number 20, we run a simulation in which the capsule and its main components are controlled remotely by the Mission Control Center. External certifications will be needed from the Federal Aviation Administration in the Office of Commercial Space Transportation to regulate the U.S. commercial space transportation industry, to ensure compliance with international obligations of the United States, and to protect the public health and safety, safety of property, national security, and foreign policy interests of the United States. To also encourage, facilitate, and promote commercial space launches and re-entries by the private sector. They also recommend appropriate changes in federal statutes, treaties, regulations, policies, plans, and procedures, and facilitate the strengthening and expansion of the United States space transportation infrastructure.
Hello, my name is Jose Rivera, and I'll be talking about the reliability, maintainability, and availability sections. So, what do these terms mean? Reliability is a system's ability to perform the required functions under the stated conditions for a set period of time. Maintainability are the system modifications that are aimed at correcting defects throughout the use, but should also refer to the low average time spent executing these preventive and corrective actions. Availability refers to a system's operational availability through its use and measured against the system's downtime. For each of these systems design attributes, a program and/or plan exists for the relander system, and is depicted in this image. The increased reliability and proper maintenance produce a higher system availability. So the RMA program plans. The reliability program plan identifies the tests required to verify reliability requirements with minimal acceptance runtime of a service. So during these integration and implementation times, the communication systems will be tested to ensure proper communications with the duration partially equal to that of the expected flight time, and the same will be done for the propulsion systems. With this data, the test examples will be taken to predict potential failures of the system and ensures the specifications are met. The maintainability program plan reduces the maintenance cost during the use phase, improves operational readiness, and analyzes the data to provide the time to repair and failures. The plan documents the maintenance activities required leading up to the system launches and the activities to be executed after a safe landing. As the maintenance is done on the different subsystems, data is captured that identifies when certain components are replaced. With these recorded times, we can calculate the mean time between failure and the mean time to repair. Continuing the program plans, the system availability increases with both reliability and maintainability are managed successfully and documented into a plan just as the IVVT plan. The availability of a system can be quantified by using the two previous attributes, mean time between failure and mean time to repair, with the equation shown on the slide. The increased availability of the system ensures the success of the company by providing the high confidence to the user. Along with providing a proper plan, the system availability increases by adding redundancy to the most critical system. Some of these systems may be the communication and life support systems. These are captured as specifications that will provide additional insurance for the safety and completion of the touristic mission. These RMA system attributes of the relander system provide the basis for the proper usage of the system in its intended environment throughout the use and maintenance phase. So, the system usage phase. Once the relander system has been certified by the proper certifying authority, the system enters the use and maintenance phase. The system will operate in its intended environment, such as the conditions specified. The system will launch in the most optimum weather. The fuel and communication systems, among others, must be verified and tested 1 to 2 days before launching. For the rocket launches, the communication relays will be scheduled for support of the critical event. When the rocket launches and reaches the orbital distance, the capsule will be released to commence orbiting the Earth. The pre-established path will be followed by the capsule in order to provide the astronauts the enjoyable astro experience. Once the rocket and capsule both re-land on Earth, the RMA program plans are to be executed in order to properly maintain the system along with the maintenance tests. This cycle is repeated throughout the usage of the system. And finally, system disposal. After the indicated and/or recommended end of life for the system has been reached, the disposal plan is to be executed. This provides the recommended efforts towards dismantling the system into the different subsystems and components, proper disposal of the complex system by the components, recycling and salvaging any reusable components such as the communications, life support, and/or propulsion components, safe handling and discarding of toxic materials along with the certification of this disposal to be provided. This is applicable to the fuel cells, waste, and/or batteries. In conclusion, the IVVT plan for the relander system identifies the following for the rocket and the capsule, such as the component testing strategies for the communications, propulsions, and life support systems, the built-in testing and reporting of the systems, integration testing of the subsystem as they come together, qualification and acceptance of the system by the customer and certifying authority, the use and maintenance testing activities throughout the life cycle, and finally the proper disposal of the system. With all the elements included in this plan, the system is adhered to this plan as the subsystems are designed, developed, and integrated. This plan provides the proper documentation and records the results for the different testing verification methods.